So our next talk is going to be Antonio Prados from Universidad de Sevilla. And he will tell us about building and optimizing finite-time adiabatic processes in stochastic thermodynamics. Tony.
Thank you. First of all, I would like to thank the organizers for giving me the opportunity of presenting my work here at this exciting conference that it is about to finish. And this is a work that I've done in collaboration during the last year with these people, Carlos Plata, who is now at Padova, and Guéry-Odelin from Toulouse, and Emmanuel Trizac from Paris. This is an outline of the talk. I'll start with a brief motivation of the work, why we are interested in this kind of thing. And afterwards, we'll move on to the building of these finite-time adiabatic processes, showing that they are indeed possible, and that, interestingly, there emerges a minimum connecting time between equilibrium states. Afterwards, I will briefly look at another related problem, which is that of optimizing the temperature, okay? And of course, I'll end with some conclusions. Well, the motivation starts with the system that we're interested in. It is very simple. It is a colloidal particle that it is trapped by laser optical tweezers, for instance. And this experimental setup makes it possible to change the degree of confinement of this particle. You can change the stiffness by changing the power of the laser, basically, because they are proportional. So we are going to move in the overdamped Langevin description of the dynamics, and this is the typical thing with the force coming from the trap. This lambda is the friction coefficient. This T is the temperature of the fluid, okay? And then in equilibrium, this is the variance of the Brownian particle. Stochastic thermodynamics is basically the natural physical framework for doing this kind of calculations. We are with a mesoscopic system, then fluctuations are important, and so you have to extend somehow thermodynamic concepts to the mesoscale, and this was done by Sekimoto and other people some years ago. And from the Brownian particle at the average level, in the overdamped description, it is very simple. This is the total energy that has these two terms. This is the velocity contribution that, as we are in the overdamped approximation, it is always 1/2 of kBt. And this is the energy coming from the trap. And well, even at the mesoscopic scale, you have energy conservation. Basically, the first principle work is defined like this, like the change of this average energy due to the change of the external parameter, that it is the stiffness here, and heat is the rest of the change of energy, so that the first principle holds, basically. Although I'm not using this, it is interesting to remark that the PDF of the Brownian particle remains Gaussian for all times, even if we are changing the stiffness and the temperature, as we are going to do in the following. Okay, and this is the equation that makes the variance evolve in time. It is linear, it is simple, but you have to remember that this K and this T are going to be time dependent, so they are not so simple in the end. Well, why are interested in studying this kind of adiabatic processes? Well, in the sense, not in the quantum sense of a very slow change of variables, but in the thermodynamic sense of zero heat. Well, they are a cornerstone in the thermodynamic of macroscopic systems, so it seems interesting indeed to extend this kind of process to the mesoscale. They're essential for the building of irreversible heat engines, like this field has been quite active in the last few years. And some years ago, in several papers, the quasi-static limit of this kind of adiabatic process has been solved in the underdamped approximation, by the way, and this law was obtained, but this is only valid in the quasi-static limit. But to the best of our knowledge, finite time processes in this adiabatic case has not been studied at all. Well, so some comments, zero heat in average, only in average, because it is impossible to isolate the Brownian particle from the environment, from the fluid at every trajectory, so you have to be only in the, in this case, in the average value. And another interesting thing, it is quite technical, but well, I wanted to tell you, is that you don't have to heat actually the fluid in order to change the temperature. You can change the temperature of the fluid in an effective way, the temperature that the Brownian particle is feeling, by introducing some kind of shaking, as was described in this paper some years ago. And in fact, I think in one of these papers by the same group, I think in this Nature Physics, it was used this kind of shaking in order to simulate the change of the temperature. Okay.
Is there anything like temperature of a single particle?
Well, it is the temperature of the bath in which it is immersed, and it equals the average kinetic energy of the Brownian particle in the bath. Yeah. You can construct, for instance, in equilibrium, the canonical ensemble for only one particle in a bath. Okay. Well, some questions that I want to address. Can we engineer this kind of finite time adiabatic processes? Can any two states, equilibrium states, be connected by this kind of process? What are the time protocols that do the job? Because that is the interesting thing. We have to devise some specific protocols for the stiffness and for the temperature in order to get the two states connected. And of course, can finite this kind of processes, if the answer to the previous questions were positive, that they will be, can be optimized in some way. So we go to dimensionless variables, okay, and then the initial state is 1, 1, 1. I have made everything dimensionless with the initial values, and the final values are kf, the stiffness, yf, that is the variance, and theta f, that is the temperature. And we have the evolution equation, this one, for the variance, and the adiabatic condition, the zero heat condition, this one. And we want to extract things from these two equations. And combining evolution plus adiabaticity, we obtain this exact equation that tells us that y theta is a monotonically increasing function of time. And in the quasi-static limit, in which this derivative will be equal to 0 for all times, and the system will be at equilibrium at every intermediate time, you recover this result that curiously was obtained in the damped approximation, okay? But this is, everything is in the over-damped approximation. But the interesting thing is that, in general, what you have shown is that this product is greater than 1, or equal to 1 in the quasi-static limit. So this is, if you take into account that the final state is at equilibrium, this is a restriction for the connection of states. Not any two states can be connected by an adiabatic transformation. You have to have that inequality. And can be done. This is the protocols are sensible, are physical, have a physical meaning. The answer is yes. If you go to a scale time, you can derive this equation. We have labeled with 1 that is exact by going to this scale time tau that for is between 0 and 1. For the final time, you can restrict this equation, particularize this equation, and obtain this exactly, and then you construct the reverse engineering thing, the kappa and the theta that will give you everything in this way. You build a function that it is positive. Remember that it is the stiffness that connects the two states that you are interested. Afterwards, you insert the final temperature into this equation, and then you get the final time, the connecting time. Once you have the connecting time, you insert the connecting time here, and then you solve this equation for theta, that is always positive, okay? And finally, you can derive the corresponding stiffness protocol by remembering that you have the adiabatic condition. So in these 4 steps, you construct everything. What is interesting is that you can also show that there is a minimum time for the connection. If you recall this equation that we had in my previous slide, and you look at this thing, you see that this is a very simple functional that is going to be minimized by a straight line, okay? And as this left-hand side is fixed, we are fixing the initial and the final state, then when this functional is minimum, you will have also the minimum time. So the minimum time corresponds to connecting the 2 points of the variance with a straight line. And afterwards, by doing the procedure that I have told you before in the previous slide, you are going to take also the optimal profiles for the temperature and the stiffness, okay? This is the expression for the minimum time. It is, well, quite simple, and it is positive because remember that this quantity between the brackets is monotonically increasing, okay? So it is always positive. Just to show how this works in a simple example, you can take, for instance, a biparametric family of parabolas that includes the straight line as a particular case, and then, well, I can solve for B and C by imposing that I have the final value of the variance, and that this ratio between the connecting time and the optimal time has a definite value, okay? So for this case, that is, I have here labeled as the confining and cooling because the stiffness is decreasing and the temperature is also decreasing, okay? The optimal path, it is this straight line, okay? And you have 2 non-optimal paths for a particular ratio of these times. It is 2, okay, in this case. And you have these 2 parabolas that are non-optimal, okay? Remember that this is a scaled time. So in fact, if you put this in real time, this straight line would go only until the half of the interval, okay? The parabolas extend to double time. This is the same, but the corresponding protocol for the temperature, the optimal one, that it is monotonic, the non-optimal ones that are non-monotonic in general, and the optimal protocol for the stiffness, and also the non-optimal protocols that are like this. And the stiffness always in this kind of problems in stochastic thermodynamics, typically has some finite jumps at the boundaries, but this is not a problem for the adiabatic thing because they do not contribute to the heat. They do contribute to the work, but not to the heat, okay? A couple of things more. Well, we can have a look of this optimal time, this as a function of the final temperature for fixed values of this target stiffness. So in this case, that it is for the confinement, we are decreasing the kappa. This is the behavior of this minimum time, that it is non-monotonic, okay? And the most important thing is that there is a temperature. In this case, it is when the process is on top of adiabatic, it is isothermal, and you have a global minimum time, but that it is different from 0. So when you are deconfining the system, you cannot do an adiabatic process that it is instantaneous. This has been proposed somehow in the literature, but it is not possible, okay? For confinement, the situation is quite similar, but the thing is that this global minimum time is equal to 0. And this global minimum corresponds to the case in which delta y, the variance, does not change. Okay? This was not possible before because the previous slide, this vertical line, I have not told you about that, but this vertical line is the asymptote, is the quasi-static limit, and then in this kind of system, when the system is deconfining, you are always expanding. You cannot do a process in which the variance does not change for the confinement. Okay, the system can here cool or heat. In fact, in the second case, the system always heats because this limit temperature is larger than 1, but the system may expand or may compress somehow. Okay. Very briefly, the optimal temperature, a different and principal optimization problem. We fix again the initial state, but instead of fixing the final state, we can fix the connecting time. Okay, and they say, well, what is the optimal mismatch between the initial temperature and the final temperature that it can be of experimental relevance? And you can write a constrained variational problem by writing this and introducing two Lagrange multipliers in order to have these two equations, the evolution equation and the adiabaticity condition, valid, assure their validity for all times, and you do a lot of calculations that are quite simple but, well, lengthy. And after all the calculations, you end with a very simple answer. The answer is that all you have to do is to invert the relation that you obtained for the minimum time in terms of the temperature in order to get the optimal temperature in terms of the time. And why is this so simple? Well, the answer from a physical point of view is quite obvious. If this is only for confinement, the answer for the confinement is the same. If you plot again this minimum time that was non-monotonic, and you fix, this is a horizontal line fixing the connecting time, then you are what you see here is that to the left of this point you cannot go, and you cannot go because you need a connecting time that it is longer than the time that you are fixing somehow. So this is the minimum temperature. Okay, as this is non-monotonic, when you go down and you go to lower connecting times, then you have a minimum temperature and a maximum temperature because this equation, when inverted, has two solutions. Okay, so the conclusions, that is my last slide. We have shown, I hope that I have shown you clearly that this kind of finite time adiabatic processes can be rigorously built. We have dealt with two optimization problems that in principle seem that they are not related, but they are controlled by a unique function. Okay, and there are a lot of perspective, a lot of work that can be done. The stability of solutions, fluctuations are important. You are not going to implement this kind of optimal protocol in a perfect way in experiment, so the stability is important. What are the consequences for the irreversible heat engines? Because you have this kind of restriction for the adiabatic branches in which, okay, can this kind of reasoning be extended to the quantum case, because these quantum heat engines have been, it is a field that has been also quite active in the last years. And well, finally, this is the preprint. This is very recent. This is the team. I have also I would like to acknowledge my funding, and of course, thanks for your attention, and questions and comments are welcome.
Set up while we take some questions, please.
I think this whole problem can also be studied using geodesic in hyperbolic surface.
You can, I think.
The constraint is that we are taking the process as adiabatic process. So that is the constraint. And
the evolution equation.
As a geodesic hyperbolic.
Yeah. In fact, the first problem, you can also solve it by variational approach, by writing the integral of 1, that it is the increment of time, and putting 2 Lagrange multipliers, doing everything, and in the end you get the same answer. Okay, but well, the kind of approach that I have shown you here, I think it is more physical and it is simpler, no? Somehow, no?